All right, now we're back in the post lecture with Markov decision processes. We're going to dissect what it means to look at this by rolling it out over a couple iterations to start with. So we're going to say that the agent starts at a state at a particular time point, let's say t, and it gets to take an action. We're going to encode this as AT. And based on that action, the environment is going to change perhaps, and we're going to arrive at a new state, possibly, again, the same state if, let's say, nothing changed after taking the action. And we'll be in state t plus 1. And you can see where this is going. We're just going to keep on rolling. We'll get a new action by the agent, a new state, which the environment gets to inform us of. Okay, that the model can then take into account, the agent can then take into account, and then so on and so forth. Okay, so when we think about this in terms of reward, it's also similar. We saw that in the pre-lecture where we're talking about a Markov reward process, the reward is basically only conditioned on the state. But in NDP, because there are actions, it's also conditioned on the action. So given the state, the agent takes an action, and that action and state together lead to a reward, but we only observe it in the next iteration. Okay, so the RT comes actually at time t plus 1. We're informed about the reward one step later. Okay, and you can see where this is going. So we get R plus 1, RT plus 1, RT plus 2 at subsequent time steps, always one ahead of the actual timing. So once we've wrote out this entire MDP, we can see where we're going with this, right? In the upper box, we have our value function, which is being computed as an approximation for how good a particular state is. And it's basically looking at the cumulative awards over a number of steps, right? So we're going to write V as conditioned on the particular policy that we have in play at the time. Okay, now the policy also dictates the actions, which is this purple line at the bottom, right? The policy basically says, given a certain state, what type of action am I going to do at that point of time? So when we're thinking about the value function, we really need to think about not just the current reward, but the reward over multiple time steps, right? So we're going to encode this as another form of rewards called a utility or return. So the return, we're going to denote it as GT here, is the total discounted reward from the current time step t. So we're looking at being in a certain state at time t, looking at the reward that we would be getting after leaving that state, after taking a certain action, and then all of the rewards subsequent to that. Okay, so we're going to go all the way to the termination of the MDP and then say, how much reward did I get? Okay, and that's going to be the returns. Just like if you have returns on a loan or returns of interest over time, that's the same concept. Okay, you can also use the idea of utility. You know, the utility of being in a certain state is not just the immediate utility, but the utility over an entire stretch of time until the end of the problem. Okay, and we're going to add this other factor to say there's a discount, right? So the discount is being applied exponentially as a decay over multiple time steps, right? So we're just going to say I'm going to add the reward at time t plus 1, t plus 2, t plus 3, all the way to the end, where I might have an infinite number of time steps. But each time I add a reward, I'm going to decay it a little bit, dependent on this gamma factor taken to the power k, where k is the number of steps that I've taken, right? So the value of receiving this reward changes over time, right? Because, for example, a particular reward that we would get towards the front of the problem might be more worthwhile than towards the eventual rollout in the back, right? So you can see that you might get some number of money, but very far in the future, you might prefer to take that money now. Okay, so this is embodied in this discount factor. We can say that if we have a gamma of 0, then all of these exponents over here, from here onwards, they go away. Okay, we're looking at a short-sighted reward where we're only caring about the immediate reward. Okay. On the other hand, if we set gamma close to 1, if you imagine it is set to 1, then we're going to look at the entire set of rewards coming from the current time step all the way to the end, undiscounted. Right? So everything is fair. I don't care whether I get the reward now or in the future. They all sum together, and I prefer the maximum of that. So, this idea of having a gamma factor or a discount factor is important to understand why we do that, right? So when we think about most of the reward processes and decision processes that we come up with, they're usually discounted. And why might that be? Well, it's actually quite simple. It's actually quite mathematically convenient to discount rewards, okay? So it actually ends up being nice and smooth this way, and we can calculate things to iteration and completion. It's also the case that it avoids infinite returns from cycles. So imagine if you have an MDP like the one that we saw earlier from our student MDP, where you might go in cycles. You might go clubbing and then come back and need to study again. Then you get too depressed and you go clubbing again. And so this type of cycle will incur an infinite number of rewards, especially if there's a positive value. Okay? There's also the case that we might be uncertain about the future. We don't actually know whether, even though we have a completely specified NDP, whether it's going to work out well. Might be some uncertainty about states or values in the future, so we might prefer to get the rewards right away, just like in the case of having a financial reward. Okay, because if we have a financial reward now, we can use that money to invest and get some interest in the future. And actually, animals and humans exhibit this type of behavior in the wild, right? Or in the city as well. So that this type of behavior about trading long-term gains for short-term gains is very common. Okay? So we're going to come up with this idea of a value function. The value function is basically this idea of V. It's going to give us the long-term value of being in the state S. So it's approximating that sequence of G's, right? So we're going to come up with this idea of a state value function, which is a specific type of value function, which is going to encode what's the importance or what's the utility or returns of being in a certain state at a certain time, okay? So it's going to be the expected return starting from state S, and this can be true of an MRP, a Markov reward process, as well as an MDP, right? So an MDP has the actions as well, okay? It's going to be, in the case of an MDP, we have an extra term here. It's going to be conditioned not only on the state, but also on the action, being a particular action that we pick, okay? So with that, we also need a policy, okay? So we have a value function, and the value function helps us understand what's the utility of being in a state. But we need to pick what type of action we're actually going to do. And that is going to be conditional on this idea of a policy. A policy is basically a distribution over actions in a given state, okay? So we saw that purple line before in the rollout, which said in a particular state, I want to decide what type of action I'm going to do. And we can say it's a deterministic thing, like if I'm in a particular state, I will always choose this action, but it's more easy to generalize this as a probability distribution, right? So we're going to say that in a particular state, I'm going to choose a particular action with a particular probability. And this is going to be encoded in a distribution which we're going to call pi for policy. Okay. Now, with a policy, we actually have the entire idea of what type of behavior we want our agent to do. Okay. So the important part about dealing with reinforcement learning is to then try to learn what is the right policy to take. Okay. So if I find myself in a certain state, what's the right action to do from here? Okay. So as we already noted, an MDP is actually a Markovian process. Okay, it means that each time we encode a state, it has to be taking the same action out of it every time, according to whatever policy that I've dictated. Okay, so even if we find ourselves in the same train station or in the same room, the state might be different, okay, because we're not just encoding the location, but also other information that we would need to make a decision. Okay, so when we say a policy depends only on the current state, that means whatever other factors which we use to make a decision is being encoded in that state. So now when we talk about a Markov decision process, we actually can think about two different value functions. We've got the state value function that we are inheriting from the MRP, the Markov reward process, but now that we have actions, we also have an action value function. Okay, the action value function is being modeled by what we call a quality score, okay, or Q, which is basically telling us the value for taking a particular action given being in a state. So I'm in a state, I have several different things that I can do, sleep or study, and basically based on that I get a utility value or I get a return value for that, and that's being encoded by our quality value. Okay, so it's basically an expectation of the returns, so GOT is our returns, conditioned on what state and action I take. And here's an example of a state value function for our MDP. Right? So here, this is a state value function. So you can see in the nodes themselves, we have encoded some numbers here that tell you the value of being in a particular state. Okay? And this is for the case where we have a policy that just decides to do any of the two actions that are apparent, except for in the case of sleep, where there's only one particular way we can go, we can only sleep. Either one of those actions, like to go to sleep or to study, with 50% probability and no discount at all, meaning that we want the full reward chain all the way from the end to the beginning. Okay, so you can see here at the beginning we already have a negative value because we can take 50% probability of browsing and 50% probability of studying, and based on these two different things we can average those out and we can see that our initial state has a total value of minus 1.3. And so this is the general idea that we're going to work with in this framework. Ideally, what we want in solving an MDP is to find the right policy, the optimal policy that's going to tell us the right decisions to make if I find myself in a certain state with a certain set of actions that are apparent to me. Okay? And how do I decide that? Well, I'm going to decide that based on what I think are good values for being in a state or taking a certain action. So understanding my quality estimates or my state estimates are very important for me to decide what's the right way to do that. And this comes to this idea of a generalized policy iteration, which is to say I'm going to start with some policy. It might be totally at random. Okay, and the way I estimate the quality of being in a particular state under that policy also might be at first very random. And so what I'm going to do is iterate. Okay, I'm going to start with this policy pi 0, iterate my improvement of how well I'm estimating the value function until it's optimal, and then bounce back and say, now that I know how much all of the states and actions are worth, I'm going to find the right policy to do. And then once I find the right policy from that, I'll notice that my estimates for all of the correct values for the states and actions, they're off a little bit because my policy has changed. Okay, so I now have to go back and iterate and change that until I have an optimal way of characterizing under that particular policy how well those states and actions actually reward us in terms of overall return. Okay, and this is going to iterate, and we're going to eventually converge until we find an optimal policy and an optimal value function.